So today I'm just going to talk about something that isn't actually research that I've done during my PhD. It's a project that I was working on for fun here and there. It could be the worst idea ever. It could be an interesting idea, I don't know. But it's, I think, a fun idea, and it applies basically two topics. It brings together two different topics that I worked on over the course of my PhD. One is serialization, actually. So how do I provide better sort of language integrated support for serialization in a way where it's A, performant, and B, more errors are caught statically. So I don't want to be, finding all kinds of runtime, class cast, whatever errors due to serialization. And also, very importantly, this project, this thing that I had worked on, was actually quite flexible. So while things happened at compile time, it was all based on type classes and statically composing, instances of these type classes and bringing them together and to make these pickler combinator things. But because it was so, composable, it was easy to actually also change the format, so how these things are represented. So I could actually statically generate code that would, and swap. I can easily swap in the formats. So I could statically generate basically binary, basically binary messages in line, where they're used, and JSON, things like this, right? So it was quite performant. At the same time, it was quite flexible because it allowed one to change how what they wanted to serialize was represented, and also, in at least two different ways. One in the format, and also two in sort of customizing the actual object that you wish to serialize. So this was a cool project. And the second project that sort of comes together to make this cool idea that I'm going to talk about today are these funny things called spores. So many people maybe know that closures are a little bit tricky to serialize, especially in an object-oriented language like Scala. So we had this solution called Spores, which I'll cover in more detail soon, but the idea is that these things could then be, you could basically guarantee statically that these things would be serializable always. So together, we were experimenting with these two things, the serialization framework that is a little bit faster and can give you some static idea of whether or not something can be serialized. And along with these serializable functions, to build an interesting, maybe weird little programming model that we hope one could build some kind of more functional distributed system on top of. And just due to the design of this thing, we think that this model actually simplifies things in a number of ways because, due to the fact that it's mostly persistent and immutable, fault tolerance becomes a little bit easier. Things like in-memory caching becomes a little bit easier. And because the model by default pushes more types throughout more layers of the stack, we think that debugging becomes a little bit easier as well. But like I said, I'm going to say once more, and then maybe 4, 5, 10 more times, that this is a fun little research project. So everything is currently under development and changing, and it's an idea right now. It's not like the greatest thing that existed. It's just a project. So the fundamental idea, you can kind of think about this as if it was an inversion of the actor model, but not really. It's a good way to kind of think about it to start, right? So how is this possible? How am I going to be doing this? The idea is, well, if you think about actors, they encapsulate both state and behavior, and they stay in one place typically. They don't always have to, but usually they stay in one place. So you kind of have this message handler that deals with all of the different behaviors that you want, to be applied to some state. And you can think about these actors as exchanging data and commands through asynchronous messaging. This model, which right now the operating name is called function passing, it's actually stateless, and it's built on persistent data structures. And our idea is to keep the data actually stationary, unlike actors, and to instead exchange the behavior, so send around functions over the network through asynchronous messaging. And this is no new model for concurrent processes or anything like that. It's just a different way, we think, of dealing with distributed data in a functional way. Actually, I usually like to bring up this note on distributed computing because, 10 years ago, or actually more, 11 years ago, they bring up these ideas that, the idea of remote objects were bad because differences, latency, memory access, partial failure, and concurrency make merging these local and distributed models, local and remote models, both as they say, unwise and unable to succeed, right? And they say that instead a better approach is to accept that there are irreconcilable differences between local and distributed computing and to be conscious of those differences at all stages of the design. So rather than trying to merge these local and remote objects and provide one interface, we want, in this paper 11 years ago, they argued that engineers should be able to be constantly reminded of the differences between the two and know when it's appropriate to use remote or distributed, or local or remote objects. The reason why I bring this up is because this is actually sort of a seed for the ideas that were in this model. We use the idea of function application and accumulating up function applications and sending them over the wire using like laziness or a delayed application as a way of using the network, or at least using remote objects. So this is actually in the programming model. So you might ask, okay, well, what does it look like? If I have to draw a picture of it, well, like I said, sorry, before I do draw the picture, there are two concepts. Like I said earlier, stationary immutable data and these functions that you can move around, that you can move to the data that are on different machines. So we call the stationary immutable data for now silos, and we call, like I said, for lack of a better name, and we call the ability to move these functions around Spores. This is the name that we got from this previous work that we had done earlier. So I'm going to start by describing what these silo things are, then I'll go on to describing a little bit about what these spore things are. But if I have to start with a picture, you can think about these silo. I know it's a little bit dark in here. Sorry, the slides are a little bit dark. But I hope you can see. So the idea is you can think of these things as having two parts. So a silo is actually the piece of data. It exists somewhere on a different machine typically, or on the same machine as this other thing that points to it called the silo ref. So if you're familiar with something like Akka, you have these actor refs. They usually point, this is what you operate on. This is your handle to your actor. The same is true for these silo things. So the idea is that you have a reference that points to the silo thing. You actually can't operate on the silo, and the silo reference can be, you can't actually operate on the silo, as it is. You operate on it always through the silo ref, and the silo ref can be on it can be on any machine. It can be on the same machine as the silo or on a different machine as the silo. And you can make these interesting sort of directed acyclic graphs that represent interesting computations. And you can build them up on one machine, have them done on another machine, and they can be, one of these sort of trees can actually span between different machines. So they all don't have to live on the same node. They can be broken up across different nodes. And there are three main operations on these silo ref things. There's something called apply, send, and flat map. So, like I said, the silo ref is the handle to this silo thing. And right now, I'm just for the sake of, I know it's really hard to see, I'm very sorry, but just for the sake of this example, we're just going to pretend that the apply takes two functions, or two spores, rather than just one. In reality, it takes just one, but like I said, for illustration purposes, two is going to be prettier to look at. And it returns another silo ref, so it returns a reference to another possibly remote piece of data. Yeah, that's exactly what I said. What's very important, though, is that these things this apply method is lazy. So when you use this, this thing is used to build up a graph of computations that you can then later send over the network. So it defers application of the function to the silo and then returns the silo ref with info on how to later materialize that silo somewhere else. Send is the eager operation that actually forces the thing to be sent over the wire. So this is basically the handle for network communication. So and it returns a future. So whatever the result is of this function application, it's a future that's later computed. And flat map, of course. So sometimes you need to move data around, and this flat map combinator exists. So you can send a spore to a silo. And the result of applying that spore could create another silo ref on that machine. So it's a way on that node. So as the silo ref. So it's a way of basically moving data around. And just like the apply method, it also returns a silo ref, as I said. Yeah, I just went through that. So here's maybe a little bit more detailed example. So I'm going to just iteratively get a little bit more detailed with these examples, but they're all still very basic. So let's just say we want to create a new silo and a new silo ref. If I have some silo ref of type T that points to an existing silo of type T, I can apply this function and then apply this spore and then send, which forces it to be the function to be sent over the wire to this silo, applied to this silo on the other end, and for a new silo ref to be on machine 2 over here, on the machine on the right, a new silo ref to be created. Before this whole thing is actually applied and a new silo is computed, I have a reference, I have this new silo ref over here. So over time, as this thing is eventually materialized, I could still do stuff to this silo ref of type S. And it's a handle, it doesn't even have to exactly point to something that already exists. Eventually, this graph will be completed as these things are materialized. So again, it's also important to note that these things can be on different machines. You don't have to have just one machine for, or you don't have to think about this model where you have one node that deals with all the silo refs and another one that deals with the silos. This is just for the sake of illustration. You can break these things up in many different ways. Now, the other little important bit that I'd like to mention is spores. Well, what are these things exactly? This is a research project that I had worked on basically last year. And it's all about trying to solve this trouble that we have with closures, especially in a language like Scala, but not limited to languages like Scala. It exists across all different sorts of languages and paradigms. So I'm just going to enumerate sort of some of the issues that closures have, especially when operating within a distributed or concurrent environment. So in Scala, especially in languages like Scala, it's possible to accidentally capture non-serializable variables like this enclosing this reference. So if I try to serialize something that accidentally captures that, and if the type of the enclosing this thing is not serializable, then you get a very confusing runtime error typically. There are also a number of compiler-specific translation schemes that can create implicit references to objects that are also not serializable. So you write some code and the compiler translates it in a way that you didn't expect, and there could be an implicit reference that you didn't realize is there, which also causes a serialization error. And then there's also the possibility of having transitive references that might inadvertently hold on to excessively large object graphs, which of course can create memory leaks. Nobody likes that. Capturing references to mutable objects, we can do that in Scala because Scala, is basically Java with lots of functional features added to it, right? So I can capture a reference to something that's mutable and have all kinds of race conditions happen in a concurrent setting. And also, unknowingly, one major problem, which doesn't seem like a major problem, is unknowingly accessing object members that are not constant. So certain things like method calls, which in a distributed setting can have logically different meanings on different machines. This is actually problematic. And to give you 2 quick examples of some of these problems. So this is something that does happen in Spark. So I don't know if anybody is familiar with Spark. It's basically, it attempts to try and improve on Hadoop by A, being a lot nicer to look at and being more concise, and then B, doing things in memory so it's a lot faster. Has anybody seen or used Spark? Are people familiar with it? Okay, cool. So you can think of, in Spark, this RDD thing is basically like a distributed collection. It's like a distributed array. So if this array is too big to be in memory on one machine, you can have bits and pieces all over the place. You treat it as if it's one array. And you can call a number of higher order functions. You can use there's a number of higher order functions that you have access to, like map, which of course applies the same function across all shards of data on your cluster. But the problem here actually is in the function that we pass to map. So we have this enclosing class, this myCoolRDD app, which, as you can see, it doesn't extend serializable if we're going to use Java serialization, and it captures this param thing here. So this closure captures this param thing here, and actually this in this case, Spark ends up crashing with a not serializable exception because myCoolRDD app is not serializable. So this is a normal problem that looks totally innocuous. It looks totally fine, but of course when you try to run the code, it doesn't work. A logical problem that sometimes happens is at one point it was happening in Akka. Basically, the idea was if you mixed actors and futures, sometimes you had this funny problem, this funny logical issue, due to the fact that futures are closures, basically. What would happen is, so this is a message handler, and this is a certain, this is this receive message, and you have this request, this handler for this request thing. And let's just say it takes a really long time to compute whatever should be done to this request message type, right? So, of course, being a smart programmer, we're going to wrap it in a future because that throws it off to basically usually another thread, and then it takes some time to compute over there. And when it's finally done, then we finish. Oops. Then we basically, if we put it in the future, we can free up the message, the actor, to move on to the next message. So what happens is that this immediately returns before actually this code is executed, and the actor goes on to handling another message. So what could happen in this case is that let's just say there's this in this example. After we compute this long-running result, we want to send another response back to the person or to the actor that originally sent this message. So what can happen in this situation is that since this code is executed later somewhere else, the meaning of this sender thing can change. So if the actor moves on to processing another message, sender is now someone else. So if Mary sent Tom, so this actor is Tom, if Mary sent this message that we're processing now and says, okay, send it back when we're done, and then we throw this off into a future, and then we start handling a new message from Bob. Basically what can happen is when this is finally computed, this actually means Bob now. And so Bob receives the message that Mary should have received. So these are capturing issues, basically. So Spores are a closure-like abstraction and a very lightweight little type system designed for use in these kind of environments. And really the overarching goal is well-behaved closures that can control environments and avoid various hazards. And this is basically achieved by enforcing a certain syntactic shape, which dictates how the environment should be declared, how the environment of a function or a closure should be declared, and then providing a little bit of additional type checking to ensure that types being checked have certain properties like serializability, for example. And it's really the most important point here is that Spores encode extra type information corresponding to the captured environment in their type. And so this is the really ugly longhand version of what these things look like. The basic idea is that there are two parts to these spore things. So first you have this kind of this keyword looking thing, but within it you have both this first part, which is a sequence of local value declarations. So in this case it's just one, and this represents the actual environment of the function. This is that this spore is allowed to kind of capture and carry around. And then you have the actual closure itself. And basically the rule is that this thing is allowed to capture anything in its header, but nothing else. So if it reaches outside of this scope, then you have a problem, and you fail to compile. So that's a very simple little syntactic rule. It can actually, so like I said, this is the longhand ugly version, but it can be made more concise, and I'll show you in just a second how. But what's nice about this is that it requires all captured variables to be declared in the spore header, so you can't accidentally capture all of Wikipedia by calling Wikipedia at length. It doesn't actually pull in Wikipedia, it actually computes the length and then captures that. So like I said, yeah, so the initializers of the captured variables are then executed only once, which is upon creation of this function spore things. And then references to captured variables, also another benefit is that the references to captured variables don't change over the course of the Spores execution. There are a number of rules about what can be in this header thing here. So of course you can't have vars, so references that can change over time. Nothing can be lazy up there, and that just means that your environment is kind of effectively immutable. And it's also important to note that the evaluation semantics are exactly the same as if you didn't have this spore thing in there at all. So if I remove this spore thing here, these two pieces of code are evaluated exactly the same. I don't do any rewriting at compile time. I just do some extra checking. And like I alluded to, there are these coercions from this from normal closures to spores. So it's easier basically to include these things in existing APIs. So function literals can be then regular function literals can be implicitly turned into a spore if the function literal satisfies the rules, which means it doesn't do all kinds of extra capturing. Oops. So just to summarize a little bit, so this is the highlights of these spore things. But just to summarize, some benefits of these things is that the environment, these captured variables, is declared explicitly, and due to these rules where these things can't be changing over time, it's basically fixed at the time that the spore is created. So it's an effectively kind of immutable environment, and it's possible to statically ensure that everything. So these spore things, because you can also ensure. I didn't show you exactly how, but it's possible to statically ensure that everything is captured has a certain property, for example, being serializable. So I can attach something called a property to these things. And that makes it possible for these things not to be so dangerous when they're being shipped around a network, and also to make sure that everything that they capture or reach out and do, it's always serializable, which is, of course, very nice if you're trying to send these things around the network. There's a paper that we published last year, and also, with a type system that goes further and talks about excluding certain types and things like this. But what's maybe more friendly to read is the Scala improvement proposal that we put together on the Scala documentation website. Okay, so those are the two pieces. Like I said, there was these silo things, these data containers with references that could point to them called silo refs, and there are these spore things which I know I can serialize and send around the network. What kind of programs can I build with these things? So I have a cute little example, and it's very, very limited because it's actually really hard to visualize these things, I noticed. So let's just pretend that we want to implement a little distributed list, a little Spark-like thing that has two operations, map and reduce. So this is to just give you some picture of how things would be looking underneath the hood if I already had the logic for map and reduce, and I wanted to basically do a little map reduce on one of these distributed lists that I've created. So this is again all happening kind of on two machines here, but you start by using this apply method, and in these, so these are all silo refs. So let's say I have a base piece of data, a base list that I want to then apply some transformations to. So I can use this silo ref thing. I already know what the logic is for this distributed kind of map thing, and this f would be what the user supplies. So this would be the function that we would pass to map. Like I said, this doesn't have to be two separate things. This can all be one. But just for the sake of illustration, imagine that there are two. And let's just say I'd like to do a few more. I'd like to, apply this function f, multiply everything by 2, and then just reduce and sum everything, right? So this is the logic that I would like to build up and apply. And I can do this over time, and I can build up this DAG. And also, like I said, it doesn't have to be just one chain of operations. I can also take, if I knew the reference to this thing, I could start applying stuff from this node here. I can start using a different map or whatever else, and I could build a DAG. I could build a DAG that also spans between different machines. But what's important is that now, let's just say I would like to basically do this reduce thing. I have to use this eager send operator here, which at this point, assuming that this base piece of data is already materialized, what the send operation does is it forces basically all of this stuff to be applied together, okay, and sent over the wire. So this arrives wherever this piece of data lives, and I know that I have to apply these things. I can also get rid of intermediate data structures. There's ways to do that, but for the sake of this example, I'm just going to say apply these functions one by one, okay? And I get these intermediate silos materialized, which all reference each other and also make another kind of DAG. And when this is done, I've created, so as you saw, so this is a map, and a reduce, so I end up with several intermediate data structures, one representing a list, one representing a list, and then the result of this reduce is just is a silo of integer. And because send returns a future, when this thing is eventually completed and this integer is eventually available, it's basically sent back, and the return type here is a future of int. So if I had val, all of these operations together, the return type of all that whole expression is going to be a future of int, and this eventually gets completed with whatever is computed remotely and returned. So you might ask, okay, I mentioned earlier that this could help in sort of fault-tolerant situations. Well, it makes fault tolerance pretty easy because silos and silo refs relate to each other by the means of this persistent data structure. So you're doing everything as basically transformations on a DAG. And you're basically applying functions to data, and you're leaving the data where it is. And actually, this DAG of function applications represents basically all of the computation that you want to do to this distributed data structure. So you can, from the land of databases, you basically have these things called lineages. And so just traversing the silo ref data structure, even the silo data structure, you can end up with one of these lineage things. And since the lineage is composed of these spores, that you can serialize them. That means that you can persist them on the machines that they're on, or transfer them to other machines, and you can come up with all kinds of different strategies for handling failure. Okay, so that's the basic idea. So you might ask, well, what's the status? We have an implementation of this model. It's a little bit richer than I showed to you. I don't actually think I put the URL up there. Maybe it's on the last slide. But the whole project is just called FDashP. It's a horrible name, I know, given that it's the same as functional programming. Sorry, but this is the working name of it now. But on the Spores side of things, we had a limited prototype implementation until February of 2015. That Wrap actually changed quite a lot. Since then, we've released several times. We have an expanded test suite, and we have a new module called Spores-Pickling, which basically brings together both the spores as I described them to you, and this pickling framework, so that you can ensure that spores are pickleable, if that's somehow clear. We have a lot more implementation experience since we actually wrote this zip, and we plan to update it soon. But if you would like a more detailed description of what is allowable in these spore things, you can find that here. It's on the doc website for these things are called SIPs. They're Scala improvement proposals. That's listed there. So that about covers it. So this, like I said, it's just an idea. It's something that we're playing with. And to summarize kind of what it is, it's the idea is that you have these data, the data in these things we call silos, managed using a persistent data structure that can span different machines, and all operations, including the ones that we provide that could be provided by prospective system builders are spores. So everything is serializable, which means it's easy to keep track of what's been done and to build up a record in case you have to recover from some kind of failure. So we think it would be easier in a situation where you can make your problem mostly immutable, or you have a way of recomputing from some base piece of data, that it would be simpler to build mechanisms for fault tolerance. Oops. But that's about it. So if you guys have questions, I'm happy to go through them. Thanks.
We got 10 minutes for questions.
Oh, wow.
But you have to repeat the question.
Sure, I will do my best to actually do that.
Any questions?
Yep, go ahead.
So this might be prematurely getting into implementation too much.
Sure.
But it seems like there's at least some possibility for, if you have some long computation, you compute more and more of these silos, you can have some garbage collection problem.
Oh yeah, sure.
When are they safe to do that?
So right now, I don't do anything to, so this was actually a discussion that we've had many times before. So let's just say that you have a, something where it's a long-running computation, and you just, every day, maybe you create a new node or whatever, like a new silo on the same machine by just default, by whatever your job is. So if I computed something like 3 weeks ago, and every single day I make a new one of these big silo, I'm sorry, I just realized I didn't repeat the question. I will try harder next time. So, you could have many of these intermediate data structures that are no longer necessary. But the only problem with that is then that if you just look at this like a persistent data structure that evolves over time, if you start sharding off pieces of it, then it would be difficult to ever, then you have this nice guarantee where you can rerun computations on, just given some persistent piece of data that you start with. So it's actually like a fundamental disagreement that I keep having with my co-author, basically. What we should do about this, I think that we shouldn't do anything about it, my opinion, but not his, that we shouldn't really do anything about it. And since we have the ability to just compose functions together and kind of stage things yourself, you can get rid of intermediate data structures yourself. Maybe not if your computation is a job that computes a node every day or something like this. But in a situation where you can basically get rid of senseless intermediate data structures by doing your own kind of staging, by saying, okay, well, I don't need to go apply map 7 times. I can basically compose these things together and apply map once. Then you can get rid of intermediate data structures and save memory by yourself. But yeah, this is basically a design discussion at this point, exactly what to do. It's in debate phase. If you have an opinion on it, I'm happy to hear it. Anybody else? Yep.
So half of this is not a question, it's just an observation.
Okay.
But you began by referring to this class of work that says you need to think about what's going on in the distributed setting.
Mm-hmm.
Of course, one of the hard things to think about is how do you minimize communication? And one standard way of doing that is keep all the data in one place and send stuff to it.
Yep.
So what I really like about what you're doing is that it plays to that strength in building distributed systems. It lets you think about where you want the data to live.
Yep. Yeah, that's
I like that aspect.
cool. I'm happy you like it.
Do you want to repeat the compliment?
I can repeat the observation. The observation is that one way of, so I'm probably going to get this wrong, so you can, of course, interject if I didn't rephrase it correctly, but that one way of dealing with this problem that I brought up earlier about the difference between remote and local computation is you can always kind of reduce this problem by keeping as much data in one place. And this model sort of fundamentally kind of encourages that, or does that by default a little bit, and requires you to move data specifically if you need to via this flat map thing, actually. Is that about right, or did I get it wrong?
No, you got it right.
Okay.
It's even stronger, right? You're letting people tackle the fundamental design problem, which is thinking about where you want to keep the data.
Right, so it allows people to fundamentally tackle this design problem where to keep the data. Just to repeat it for the remote.
And then the question was, you talked about sending off a function to a silo,
Mm-hmm.
and that their persistence, you create a new silo.
Yep.
Does this leave you with an issue of garbage collection?
Yeah, so this is what I was kind of discussing just, sorry, I'm so bad at this. So the issue, so is there an issue with garbage collection when you basically end up in a situation where these things are creating silos remotely? You could have many of them, for example, on one machine that makes you run out of memory and everything crashes and it's horrible. So the answer is yes, this is a problem. But then again, the issue, basically the trade-off here is, well, we allow you to stage computations. So you can use this apply thing to kind of, in this example that I showed you, I made basically an intermediate data silo for each apply node, but there are ways to basically compose all of these things together and do basically come up with one node. So you can compose all your functions and then send them over the wire and do your own kind of staging and reduce intermediate data structures. So that's one solution. It's manual though. The benefit to this solution is that you don't have you can always sort of assume that you can safely reconstruct your entire computation from some piece of persistent data and don't have to worry about pieces from last month going away because of some kind of garbage collection on your persistent data structure. So it's a fundamental sort of, I don't know, discussion right now about should we do something about this, and there's this trade-off where basically you kind of lose the ability to do this nice fault tolerance if you start removing pieces of your data structure, if you start removing some of these silos.
So out of curiosity, what's in a reference? Presumably, if you can only send deterministic computation, you can just add the reference with a lineage of all you care with given value.
So the question is, like, what is the reference? If this reference is somehow deterministic, then actually.
A pointer or just an address? Presumably, you could sign
Oh.
computation.
Oh, you're asking what the silo reference thing is. Well, I mean, this thing, in its implementation, it's really very similar to these actor reference things that we use in Akka. And it really just contains kind of like information about where this thing is, and it's a little object that has all of these methods that you can call to queue up all of these operations. So you make a little DAG with these kind of silo ref objects. It really just contains information about where to find the actual data. That's all there is to it. Yep.
You mentioned Spark earlier. What you described sounds quite similar to Spark. Could you maybe expand on what's
Yep.
different about this?
So the observation is this sounds really similar to Spark. So what are the differences? It's actually, so you're right that you have something, and I can call like map or reduce on whatever that thing is, and it creates this lineage-like thing. That's where it is similar to Spark. Spark is an enormous distributed system, which is like this big. And this thing that I'm proposing is something that's much smaller, kind of like a middleware that would be actually more useful underneath something like Spark. So if this model existed before Spark existed, this would actually be useful for a number of problems that exist in Spark, namely the capturing issue and also the fact that everything is typed. You have typed communication. So I was actually at Databricks for a little while trying to solve some serialization problems that they were having. And if I had just a little bit of type information anywhere in the middle of this enormous stack of code that they have, there could have been so many things that could have been improved. But just because it's an enormous stack of code with many different people with different sort of typing disciplines all working together, you have different parts of the code base that wander away from this typing discipline. And this model would enforce basically more levels of the stack to be better typed, in my opinion. And also a lot of communication errors trying to figure out, oh, some actor sent a message to somebody and the whole system is hanging and we're wondering why. It's because that guy didn't actually receive that message and we didn't, he didn't, or another guy received it and there was no message handler for that type and everything just waits and times out, right? So it basically is something that you could build something like Spark on top of, but not Spark at all. Yep.
In your example, you were sending data or functions to silos on one machine, if you were to say on 3 machines.
Yep.
When you get to that reduction phase, does that all have hidden behind the silo ref, or how you?
Okay. So to try and summarize your question, you said, okay, in this example, there were just 2 machines. And what if I had these things spread around more machines? What about reductions, right? Is this all handled by the silo refs? Right now, yes. I have to say that this is part of the implementation where we're doing this bookkeeping right now for you. So yes. So, okay, it's a little bit more difficult to explain. We don't provide much more for you beyond just that. But in the example where I made like this little distributed collections thing, there's a lot more than just this little picture. So there is bookkeeping that has to be done about how to do these reduction trees. You can do them with silo refs. And this is some bookkeeping that we had to implement, which was not fun, in this layer that we built on top of this little model. So that's in the layer of the thing that says what reduce means. Because we give you send, we don't give you reduce. You implement reduce yourself. as much as, I just said, assume that you have a reduce operation, and the reduce operation has to figure out how to do a reduction tree given these silo things. Yep, okay, so I think that's it. I think we're out of time. Thank you, everybody, for coming and asking good questions.